Hello everyone! So today we're going to look at momentum in two dimensions. We're going to look at a few example problems really just to solve this one, and we're going to deal with the fact of what do we do if we've got something that happens in two dimensions. So a two-dimensional collision, collision in two dimensions is something like follows. So let's say we have a red ball, let's say, and it's traveling with a certain thing, strikes another ball, so that's say but slightly off center. So that after the collision, so this is before and this is after. After the collision, the red ball sort of travels off at an angle. So let's say it's got an initial velocity of u, and it's got an initial mass of m, and this has initial velocity also of u, which let's say it's 0, and this has got a velocity of m. Essentially, what will happen is the red ball will travel with some now final velocity v at an angle. The blue one is going to go at a different angle with its own final velocity, and is also going to be traveling at its own angle. And the idea is that the momentum before, the momentum after must be the same. Now, this problem might look complicated, but we can actually just remember that we can deal with momentum as it's a vector in different planes. We can actually start off, we can think and say, well, actually, we can treat the momentum, we can sort of consider the momentum in each plane separately. Okay, because it has to be conserved in each. And what does this mean? Is like, well, initially there is only momentum in this, in the sort of the x plane. So this sort of this plane. Okay, there's our x plane and there's our y plane. So initially there's only momentum in this direction, which means that overall there must only be momentum in this direction afterwards. Okay, so initially what we have, let's say this is actually stationary. Let's say u is equal to 0. Okay, our initial momentum, okay, our initial momentum in the x direction is equal to mu from the red ball. Okay, and that must mean that our final momentum in the x direction, even though these balls are going off in some other different ways, well, that's also just got to equal mu. Has to. Okay, so these two must combine to give us whatever the same value is. And the momentum in the y direction, well, there is nothing moving in the y direction, 0, which must mean that afterwards it must also be 0. And that is something that we can now do. We can solve this, we can solve these problems rather by just basically thinking about the momentum in each plane. So let's consider a kind of so let's consider this as an example. It's easiest to work through this as an example. So let's deal with these things. So let's say we have a red ball which is moving with an initial velocity of 6.0 meters per second. And it's going to collide with a blue ball which is stationary. And we're going to give this one a mass. We're going to give a mass of 2.5 kilograms, and let's just be easy, let's make them the same mass. Let's make that also 2.5 kilograms. Now afterwards, what we're going to see afterwards is the red ball is going to be observed moving in this direction which is at an angle of 30 degrees to the horizontal with a speed of 5.2 meters per second. The blue ball is going to be seen moving sort of that way with a speed of 3.0 meters per second. And our question is, what angle is it moving at? Okay, that's going to be our question. What is theta? Now, one of the nice things about the A-level way that the A-level problems are is that this actually is solvable via considering either in the x direction or the y direction. You can immediately get to the answer. We're going to do it both ways because we're going to see that you get the same answer. But because of the nature of these momentum problems, which have to be chosen quite carefully, in terms of otherwise you end up with contradictory information, because if you just pluck numbers out of thin air, you'll end up with something which is contradictory. So what we're going to do is we're going to say, okay, so we end up, the simplest ones tend to be, or the ones you often get, is one where you actually can apply either equation. If you have to be more confusing, let's say you don't know this and you don't know this, you just have to, it just takes a bit longer to solve, but we'll do one of those in a moment. So we can consider our initial momentum, and we can do the x. So let's consider the x direction. So the initial momentum is equal to 6.0 times 2.5 plus, and we've got nothing from our blue one, 0. And that equals 6.9255 is 15. Okay, so that must mean afterwards we've also got to equal 15 kilogram meters per second. So what do? Well, we have to resolve this to find the momentum in each direction. So we've got 5.2 times 2.5 for the mass times velocity, but cos 30 because we're at an angle. So we've got 2.5 times 5.2 cos 30. And this is going to be added to 3.0 times 2.5 cos theta. And helpfully, I've not drawn, even though I've got these sort of nice things, I've not drawn the same level. So that's excellent. Oh, it's an angle. That's just upsetting. So this just becomes numbers. 2.5 times 5.2 times cos 30. If I type that into my calculator, I get 11.26. Okay, I'm 11.26, and 3 times 2.5 is 7.5. And that's equal to 15. So I can then just say take that over there and divide through by 7.5. So I end up with cos theta is equal to 15 minus 11.26 over 7.5. 15 minus 11.26 over 7.5, and I get 0.498. So essentially I'm getting 0.5. So 0.49, that's 499. It's basically 0.5. The reason it hasn't come out perfectly 0.5 is because that was a much longer number. So if I therefore do the inverse cos of that, that gives me theta is equal to 60 degrees. Boom. Well, that's lovely. Gives me an instant way of working it. Now, the other way that you can think about it, and it should give us the same thing, is we can consider it in the y direction. In the y direction, okay, the initial momentum is 0 because there is no sort of like that. If you've got one thing moving, it's moving the x direction. So nothing is moving the y direction. So what that means is that the vertical velocity, the vertical momentum of the red ball has to equal the same magnitude as the vertical velocity, the momentum of the blue ball. So it must mean that what that gives us is that, so let's do, our red one is now 2.5 times 5.2 sine 30 must have the same magnitude as 3.0 times 2.5 sine theta. So what we end up with there is 2.5 times 5.2 times sine of 30 comes out as being 6.5. So I end up with 6.5 over and 3.05, 7.5 is equal to sine of theta. And if I do that again, 6.5 over 7.5 sine, that I get 60 degrees again. Excellent. So theta is equal to 60 degrees. So it's actually quite nice because it means that we can take this in either direction and we say, oh, okay, that's kind of fun. It's always quite nice. So that is one sort of helpful way of doing it. And often A-level problems are actually set up in such a way that you've been given actually almost all the information of this post-collision world. Okay, because that allows you to approach the problem in either way. You can either approach the problem by by doing a very simple resolving in either direction. So you can resolve it that way. You can resolve it that way. You can also draw you can actually draw it as a sort of as a triangle. So you can draw it as a scale sort of thing because you know that the this initial momentum, which is 15, you've got to end up at the same place as if you do the red one followed by the blue one. Okay, so that that one then that one has to equal. So if you can do a scale model and you can say, oh, that's at 30 degrees, and you can sort of, you measure that out. You can do it that way. If they give you graph paper or squared paper that allows you to do it, to draw it as a scale, but it's fine. It's simple because often it's about saying, well, they don't want you to go to town on it. So let's do an example where we go to town on it, just to show you how the conservation of momentum thing is a perfectly solvable problem, but just involves taking the steps through several times. Okay, so let's make this as nonsensical as I can. Okay, so this is going to be a slightly longer example. Let's take our red ball. Let's say it's moving at an angle. It's moving, let's say it's traveling at an angle of, let's say that is 20 degrees. Okay? And it's going to collide with a ball that's traveling in the opposite direction. And let's say it's coming down at an angle of 10 degrees. Let's make the mass of this one 1.4 kilograms. Let's make the mass of the red one 2.9 kilograms. Let's say this is moving with a velocity of, let's say 3.7 meters per second. Let's say the blue one is moving downwards with a velocity of, let's say 1.3 meters per second. And that's our initial thing. Now afterwards, I'm going to tell you what one of them is doing. So let's say afterwards we know what the blue one is doing. It's the lighter one, and let's say the blue one is going to be seen a little bit afterwards, and it's going to be now moving that way. Let's say we're moving an angle of let's say we're moving an angle of 17 degrees, and we're traveling at let's say 1.4 meters per second. Okay, so that's what we know. We know that, we know this, but we have no idea at this point what is our red ball doing. Okay, probably the best guess I can go is it's probably going that way still, because everything was going in that direction, and it's probably still going upwards, but I don't know. So I want to know how fast is it going and what angle is it making to the horizontal. So we can work through this problem to try and work out what our red ball is doing. So let's work through how we would approach this problem step by step. Okay, so let's take first, let's say, the x direction. Okay, so we've got now they're both going in the x direction, which is great. So we have a momentum in the x direction, 1.4 times 1.3 times the cosine of 10. 1.4 times 1.3 times cos of 10. And we've also got going in the x direction, because our red one has got momentum in the x direction, 2.9 times 3.7 times cosine of 20. Okay, now they are just numbers, so we can just plug all that in and we get a value. So 1.4 times 1.3 times cosine of 10, and we get 1.79. So I'm going to hold a little bit more, so 1.792, and our red one is 2.9 times 3.7 times cos of 20, 10.08. So we add them together, and we get 11.875. So we've got 11.875 kilogram meters per second is our momentum in the x direction. And that must be the momentum in the x direction afterwards because of these things. So let's go work out what we've got. So afterwards, what we have is we know that our blue one is going 1.417, and it's still got a mass of 1.4, so fantastic. So we've got 1.4 times 1.4 times cos of 17, and we have 1.874. So we've got, afterwards, we've got 1.4 times 1.4 times cos of 17 is equal to 1.874. So that means that my red ball, okay, so this ball, the momentum of the red ball in the x direction is equal to this minus this, because whatever this is plus whatever this is should equal my x momentum. So that is going to equal 11.875 minus 1.874. Oh, that's nice. And we get 10.0006. So we've got basically that's equal to 10. That was not intended. Now, we could actually add this to our little diagram. So we know that it's got a momentum in this direction, and the value of that is 10 kilogram meters per second. That's my x momentum from my red ball. Now we'd have to do, oh, no, don't drag that. Now we have to do it in the y direction. Now, basically, we've got to be able to do the same thing, just in the y direction. And this is why you don't get problems like this in an A-level paper. Because if you can do it here, then you can do it everywhere else. But this just, we now have to do the whole thing sort of a bit more. But in this time, instead of, and it's the same thing, instead of coses, it's sines because we're stretching the angle. So we end up with 1.4 times 1.3 times sine of 10. And I'm going to just work that immediately. 4 times 1.3 times sine of 10. And that gives us 0.316. Okay, and then we've got to add that in the y direction. We've got, we would have 2.9 times 3.7 times sine 20. So we've got 2.9 times 3.7 times sine 20. And we've got 3.66987. Oh, great. So I'm going to go with 3.670. So 3.670. Now, oh yes, because the blue one's moving down, isn't it? Yes, so the blue one is moving down. So these are working against each other. So, oh, nearly forgot, that is a minus sign because they are going, the blue is going down, red is going up. And so I'm going to say, okay, so I'm going to have to minus them away from each other. So 3.670 minus 0.316. And I've got a grand total of my y direction momentum is equal to positive, so it's going up 3.354. kilogram meters per second. So let's work out what we're doing afterwards. So afterwards, our blue one is seen, and haha, remember now it's moving upwards, so it's taken, oh, that's exciting. So our blue one has momentum afterwards of 1.4 times 1.4 times sine of 17. So 1.4 times 1.4 times sine of 17, and we get 0.573 kilogram meters per second. And so what we have to do there is say, okay, we're doing the same thing again, but this time this is our initial in the y direction. This is what the blue one has. So the red one, so the momentum of the red ball in the y direction must equal 3.354 minus 0.573. So 3.354 minus that, and we've got 2.781. So 2.781 kilogram meters per second. So now we can go back to our little finish thing, 2.781. So we know we're going upwards. And the value of that one is 2.781. So how do we solve this problem? Like how do we combine them? Well, good old Pythagoras. Because what we have is, we can think of it as going along, excellent, that's by 10, up by 2.781. And so our resultant momentum from combining that has got to be in that direction. So we end up doing there is the final momentum, the momentum of this object must be 2.781 squared. So it's the square root of 10 squared. So I'm just going to call it 10 now. I'm not going to worry about all the little decimal places that are miles away. So 100 plus 2.781 squared. So I've got square root of 10 squared plus 2.781 squared. So it's basically 107. So square root that, and I've got 10.38. So that's 10.38 kilogram meters per second. If I want to know its velocity, so how fast it's going, velocity is equal to momentum over mass. So I just divide through by the wonders of, what's the mass? 2.9 kilograms is the mass of this object. So divide that by 2.9, and eventually, we haven't actually finished the question yet, 3.58 meters per second. So it's now going a little bit slower. Hooray! But have we actually worked out the whole answer? Well, no, we also want this angle. So what do we want for that angle to be? Well, to solve that, we would have to say we can use, this is opposite over adjacent is tan theta. We can say that tan of the angle is equal to 2.781 over 10. So we'd say that theta is equal to tan to the -1 of 0.2781. So we've got let's do that. We get 15.5. So after this collision, we know that this red ball is moving off at an angle slightly shallower, 15.5 degrees, with a velocity of 3.6 essentially. So it's slowed down a little bit, and it's now been knocked so it's a little bit shallower than it was. Now, I'm going to reiterate, that's a full problem solved using the conservation of momentum. And that is not something that I really ever expect to turn up in an A-level exam, because that's a lot of work. And the problem is that all I've really done is use exactly the same singular skill. I have just done something where I've done the X direction conservation and the Y direction conservation, and I've just done some other things. So I haven't really achieved anything, I haven't done anything that isn't actually being shown by just doing this. So this kind of example is fine, and it's where they are, because there's no point getting bogged down for however many minutes that was by just doing, by asking you to do it in multiple dimensions. So what they will tend to do, rather than give you a fully unknown particle and say, what's that particle doing? If they want you to solve it reasonably quickly, what they will do is they'll give you essentially 3 bits out of the 4 information, which means you only need to use one equation. You don't need to form a simultaneous equation, and not simultaneous. You don't need to form 2 equations and start worrying about it in that kind of way. So tends not to be, because if you've got one of these bits of information, then this bit becomes much easier to solve because you don't need to think about it in both dimensions. But that's conservation of momentum in 2 dimensions. And so there'll be a couple of problems up. And I hope you enjoyed this wonderful, weird sort of site of how to solve the problem like that. Not harder, but definitely longer.